What do you know about a triangle? Yes, the most simple polygon with three vertices, three sides, and three angles. However, it can be of many shapes and sizes: tall, short, upright, or blunt with an obtuse angle, sharp with an acute angle. Other than that, it can give us many useful information and has many interesting and amazing properties, of which we are going to tell. But before we start, we would like to ask you give us a like and subscribe our channel. Now let's begin. The story of triangle. Triangles and what is a triangle? Everyone knows. A triangle has three sides and three angles. However, there are many family members, of which there is the scalene triangle. With all angles acute, that is smaller than 90 degrees, and all sides differ. Then next comes the isosceles triangle, which has two of its sides equal. And the equilateral triangle with three sides equal and three angles equals to 60 degrees. However, the equilateral triangle has many other special properties and features which we will talk about later. After that is the right angle triangle, which has an angle equal to 90 degrees. Then the right angle isosceles triangle, having a right angle included between two equal arms. Lastly is the obtuse triangle, which has an angle larger than 90 degrees. And the obtuse isosceles triangle with the obtuse angle included between two sides of equal length. After seeing the various members of the triangle, in the triangle family, let's look at the angles and sides of a triangle. A triangle has interior angles and exterior angles. The angle included between its two arms is called the interior angle. So is this one, and this one. And that staying outside the triangle is the exterior angle. Here we see in triangle ABC, here, the small green angle is exactly the same as that on the right. The small green angle on the left is exactly the same as the blue one on the right. Similarly is the green one on the top and the blue one down here. And the blue one and the green one on the right and the blue ones on the left. If we flip them over here, oh, yes, they just cover up each other. That means angle A is alpha, angle B is beta, and angle C is the same as gamma. You see? Alpha, A. Alpha is the same as A. Beta, B. B is the same as alpha. Gamma, C. C is the same as gamma. However, we can see that alpha plus beta plus gamma sums up to 180 degrees. Therefore, yes, they sum up to a total of 180 degrees because they are adjacent angles on a straight line. Therefore, angle A plus angle B plus angle C sums up to 180 also. We call this the angle sum of triangle. Now, after talking about the interior angles, we now come to the exterior angle. Alpha, beta, gamma. These three are the exterior angle of triangle ABC. If we move the green one, the green pointer here, you see, it is alpha. Okay? And then it is beta. This one is gamma. You see that the pointer has just turned a complete round, that is 360 degrees. Like this, alpha, beta, and gamma. And alpha plus beta plus gamma is 360 degrees. Therefore, the sum of a triangle's exterior angle is 360 degrees. This is the sum of exterior angle of a triangle. Here we come to the next topic. In the figure, we have triangle ABC. Having X as the exterior angle, we see that A plus B plus C equals to 180 degrees because of angle sum of triangle. And B plus X also equals to 180 degrees because they are adjacent angles on a straight line. B plus X is equal to 180 degrees adjacent angles on a straight line. Therefore, by picking up B on both sides of the equation, here, if we cover this up, A plus B plus C equals to 180 degrees and equals to B plus X. So if we cover up B on both sides of the equation, we have A plus C is equal to X. That means the sum of these two interior angles, A and C, they will combine here. The sum of these two interior angles, A and C, amounts to the exterior angle X of the triangle. Therefore, A plus C is equal to X. We call this the exterior angle of triangle. So after catering for the angles of a triangle, we now come to the sides. We have the isosceles triangle. Here, the isosceles triangle has two of its sides equal. This is AC and this is BC. So it's this one. Here we see in this figure the two arms CA and CB are equal in measure. And if we drop a perpendicular from C to AB, then we have here a 90 degree, a right angle. Then we have AC equals to BC and CD a common side, and angle ADC a right angle. Therefore, these two triangles are congruent. You see that? This triangle congruent this triangle. Therefore, there's corresponding angles A and B are equal. Therefore, for an isosceles triangle, we have their base angles equal. We call this base angles isosceles triangle. So after talking about the isosceles triangle, we now come to the equilateral triangle, having three sides equal in length and three angles equal to 60 degrees. Now we see that for this equilateral triangle, we can take this as an isosceles if we look in this way. So angle B equals to angle C, and angle C equals to angle A, and angle A equals to angle B. Therefore, these three angles, they are all equal, and the sum is 180 degrees. Therefore, each of them is equal to 180 divided by 3, that is 60. Therefore, each angle equals to 60 degrees. After looking at the angles and sides of the triangle, let's see something new, the centers. There are some special points in the triangle, we call them centers. Have you heard of the 9-point circle? But today we are just going to discuss two of them, the ortho center and the yin center. So what is an ortho center? Here for triangle PQR, we drop a perpendicular P from P to QR. This is the perpendicular. Okay? And then also a perpendicular from Q to PR and from R to PQ. We can see that the three perpendiculars will meet and intersect at a very single point X. We call this concurrent, and this is the ortho center of this triangle PQR. Now we comes to the yin center. Here, yin center is the point of intersection of all the angle bisectors of a triangle. In triangle RST, the angle bisector of R divides the angle into two halves. So you see, yes, this one. Okay. In triangle RST, the angle bisector of R divides the angle into two halves. So this half of angle R, and so is this one. So this is the angle bisector. And this is half of angle S, and so is this one. So this is also the angle bisector of S. And this is also half of angle T. So is this one. Therefore, this is also the angle bisector of angle T. We see that these three angle bisectors meet at a very single point Y. That means they are concurrent, and Y is then the in-center of triangle RST. However, for an equilateral triangle we have here, this is the oval center of this triangle ABC. This is the oval center. And this is the in-center of triangle ABC. These two triangles are the same. And we see that the oval center is exactly the same as the in-center. Or we can say that the in-center is the same as the oval center. That means these 2 points are coincide. These 2 points coincide. So an equilateral triangle is so unique a one in the triangle family that we have the oval center and the in-center at the same point. The oval center and the in-center coincide. Next, we come to another special feature of an equilateral triangle. An equilateral triangle is so unique a one in the triangle family that we can tell some special trigonometric ratio just by a glance at it. Now let us consider this triangle ABC in front of us, which has sides of 2 units in measure. This angle is 60 and this one is 30. That means it's also 60. Now we can see that from this triangle, tangent 60 is equal to √3/1, and tangent 30 is equal to 1/√3. And at the same time, sine 60 degree is equal to √3. Yes, sine 60 degree is equal to root 3 over 2. Sine 30 degree is 1 over 2. Also, cosine 60 degree is equal to 1 over 2. And cosine 30 degree is root 3 over 2. So we can, just at a glance, and tell the trigonometric ratio sine, tangent, cosine of 60 degree and 30 degree just by a glance at this equilateral triangle. Now we have discussed a triangle's angles and sides, and how to find some features of an equilateral triangle. Now then, how about the area? That's simple. Area of a triangle is equal to 1/2 the product of its altitude and the base. That means 1/2 HL. The area of a triangle is equal to 1/2 the height times the base, HL. But how does it come about? Here we see that in this figure, triangle AXM, the white one is actually the same area. The area of this one is the area of triangle AXM, and it is exactly the same as that as the green one. AXD. That means the area of this triangle AXM is half of this rectangle AMXD. Similarly, the area of this white triangle BXM, this one, is equal to the area of this blue one, the BXC. Like this. So in the whole, the area of triangle ABX is equal to 1/2 of this rectangle ABCD. As the area of the rectangle ABCD is equal to the product HL, therefore the area of this triangle, this white triangle ABX, is equal to 1/2 the rectangle. That means it is 1/2 the product of H and L. Therefore, the area of a triangle is equal to 1/2 HL, where H is the altitude and L is the base. However, are there any other ways of finding out the area of a triangle? Yes. One is the famous Herron's formula. Herron's formula. We need to know the length of the sides of the triangle when we use the formula. We are not going to show the proof here, but just mention how to use it. For a triangle ABC, here, the side opposite angle A is A, and the side opposite angle B is B. The side opposite angle C is C, where an S is equal to half of the sum A plus B plus C. That means S is equal to half the perimeter. then the area of the triangle will be equal to the square root of s times s minus a times s minus b times s minus c. Therefore, if we know the length of the triangle size, then we know the area. Is that all? Not quite. There is also another formula. There is also another formula for the area of a triangle. Here is 1/2 AB sine C. As shown in the figure, h is the altitude, the height of the triangle, and b is the base. Here we have h over a is equal to sine angle C. Therefore, a sine C is equal to h. And the area of the triangle is 1/2 BH. So is equal to 1/2 B A sine C. Therefore, the area of a triangle is 1/2 AB sine C. Wow, do you need a break? There is something more we are going to tell. After going through the angles and sides of the area, we would like to introduce a concept of congruence and similarity. What is meant by congruence? If two figures is said to be congruent, that means two figures is the same in shape and size, and we can cover it up with one another. And for triangles, when two triangles are congruent, it means that, first, the three corresponding sides are equal in length, and the three corresponding angles are equal in measure. That is, they're exactly the same in shape and size. Here, we can see that these two triangles, ABC and DEF, they are exactly in shape and size, and we can cover up them with one another. You see that the size, the corresponding size, is exactly the same. Here, yes, this is AB is equal to DE. So AB is equal to DE. And this is BC. And this is equal to FE. BC and FE. And this is, so we miss AC and DF. You see that these two are congruent triangle, and their corresponding sides BCFE, ACDF, and ABDE are exactly the same, and the angles are also equal. ABC, they're exactly the same. And we found that when two triangles are congruent, and we found that there are 5 sets of determining conditions for them, for two triangles to be congruent. These 3 sets of factors for triangles to be congruent is the first one, SSS, whereas this is the side, and SAS, where S is the side, A is the angle. This means S SS, the three sides equal. And SAS, we have SA angle S. That means an angle included between two corresponding sides are equal. The third one is ASA, angle side. The side is placed between the angles. And the third, AAS, two angles and one angle is adjacent to the angle. And the last one, RHS, where R is the right angle. They both have a right angle, a hypotenuse of the same measure, and a corresponding side equal. Let's see the first one, SSS. When the length of three sides of a triangle is fixed, it is not possible for us to move the sides without breaking the triangle. You see, when a triangle has three sides fixed, whenever we move the side, the triangle breaks. Therefore, that is, it becomes a rigid framework, and you can have no movement. Therefore, if two triangles have their three sides equal in measure, the two triangles are said to be congruent. Let's look at the two triangles below. In triangle ABC and triangle DEF, here we have AB. This is AB. AB is equal to DE. You see? And CA, see this one. CA is equal to DF. And BC, this one, is equal to FE. So triangle ABC, this triangle A, let's see this way. Triangle ABC, congruent triangle DEF. You see that these two triangles are exactly the same, and we say that they are congruent. Side, side, side. That means triangle ABC are congruent to triangle DEF, having their corresponding vertex in the same order. Now we come to situation 2. Okay. In condition 2, we have when a triangle has its base fixed and the two adjacent angles also fixed, we cannot change the shape of it without movement of the arms. That is, changing the angles or the length of the base. There is only one outcome. Therefore, if two triangles have their base the same, for example AB and DF, their base the same, and the two adjacent angles, angle A and angle D one pair, angle B and angle F another pair, and the two adjacent angles equal in measurement, the two triangles are congruent. We can check this out in triangle ABC and DEF. Here, angle A, yes, this angle A is equal to angle F, and angle A is equal to angle D, and angle B is equal to angle F. Also, AB is of the same length as DF. Therefore, the two triangles are congruent. See? They are of the same size and shape. So this is angle side angle. Angle side angle. ASA. There is triangle ABC, congruent triangle DFE, ASA, having the vertex in the corresponding order. We cannot reverse the order like this. In the third case here, SAS, side angle side. We can see that from the figure, whenever the two arms of a triangle are determined, this arm and this arm, we cannot change the shape of it without changing the angle in between. Therefore, if two triangles have two corresponding sides equal and the in-between angle exactly the same, then the two triangles are said to be congruent. Here we see that for triangle ABC, angle A is exactly the same as angle D, and there's adjacent sides here, AC is equal to BF. This AB is equal to AD. So AB is equal to D. AB is equal to DE. Yes, AC and AC and DF. Therefore, triangle ABC congruent triangle DEF, side angle side, SAS, side angle side, with angle A correspond to angle D, and angle B correspond to angle E, angle C correspond to angle F, with the vertex in the corresponding order. And now we come to the fourth condition, AAS, angle side. When a triangle has two of its angles fixed and the adjacent sides determined in length, the triangle will have its shape and size determined. No other triangles can be formed without changing either the angles or the length of the fixed side. Therefore, if two triangles here have their two of their corresponding angles equal, this one, and this one, and one of the adjacent sides also equal, that means this one, AB, and this one, DE. You see that angle A is equal to angle D, and angle C is equal to angle F here. Also, this corresponding size AB is equal to DE. Therefore, these two triangles, triangle ABC and triangle DEF, are congruent. Angle side AAS. Last one. Here we come to the last case. It is a special case of SSA. Now, here we see that we have seen the case of SSS, ASA, and SAS. Also AAS. Then how about SSA? Let's see the following. Here we see that the triangle in the figure here has a fixed arm AB and a fixed angle, this one, angle A. Then how about this side BC1? We have one side fixed and one angle fixed. One side fixed, so it is S. One angle fixed, this is A. How about the second side? We can, with a second side fixed, we can have two choices. One is this one, BC1, and the other is this one, BC2. Yes. We can see that we can form two different triangles with these conditions. ABC1 and ABC2. They both has one fixed side and one fixed angle. And the other two side and the other side also the same. And in this condition, we can have two different triangles. Okay? So it is not a sufficient condition for two triangles to be congruent. That SSA is not a sufficient condition for two triangles to be congruent. However, the two cases will come to one, a unique if we have a unique BC. Here, if BC is perpendicular to AC1, then we won't have two triangles. We won't have two different triangles. We will have only one. And in this case, we don't call it SSA. We call it RHS, a right angle, the hypotenuse, and a side. And we call it RHS. We have a right angle, a fixed side AB, and another side here. You see. If it is not a right angle, we can have two choices, BC1 and BC2. But if this is a right angle, if angle C is a right angle, there is only one choice. There won't be two triangles. Okay, the one triangle, the second triangle. These two triangles will merge into one. So we call this condition RHS condition. That means when two triangles having a RHS condition, these two triangles are congruent. Just as this one here, we have triangle ABC congruent to triangle DEF. Now we come to the last topic. We will discuss similarity. What is similar? It means the figures are of the same shape. But can we tell you more exact? Yes, it means that corresponding sides are proportional and all corresponding angles are equal if they have. Here we see that these two pentagons are similar. The sides are proportional. Each corresponding sides have the same proportion. And these two triangles are also similar. And so are these two rectangles. However, in triangles, proportional sides will also have their corresponding angles equal at the same time. Therefore, to prove triangles are similar, we need to prove the following condition exists. So there is the first one, AAA, that means three angles equal. And the second one, side SSS, that means three sides proportional. And the third one, SAS, two sides proportional and the include angles equal. We first see the first condition, AAA, that means all three corresponding angles equal. If two triangles have all their corresponding angles equal, then the two triangles have the same shape, but the sides may vary. You see that this large triangle and this small triangle, they have, if this green line, these two green lines are parallel, then we have different sets of similar triangles. These two angles are equal because they are corresponding angles with between two parallel lines. So are this pair, so are this one, these two pair. Therefore, if two triangles have all their angles equal, they are of the same shape and they are similar. So you see that these two triangles, this angle F, this angle C. So angle F is equal to angle C. Angle D is equal to angle A. And angle B is equal to angle E. That means these two triangles are similar. So we come to the next one. SSS. This means that all three corresponding sides of two triangles are in the same proportion, and they will remain in the same shape, and their corresponding angles will not change. For example, their corresponding sides for these two triangles, their corresponding sides will remain parallel here. You see that when one of the side here, for example, if one of the side AB, if these two triangles are similar, then if one of the side reduce, the other will change in accord. When one of the side, for example, AC reduced to its half here, so are the other two sides. You see, CB was reduced to its half, AC was reduced to its half, so are AB. AB also reduced to its half. And here, when AC extends to double its size, so are BC, and also AB. So if one side is doubled, the other side will change correspondingly. So this triangle A are similar to ABC, and they also have the angles. This is angle C, and this is angle A, and this is angle B. These two triangles are exactly the same. We see that here, angle D is equal to angle A, and angle C is equal to angle F, and angle B is equal to angle E. Then these two triangles are similar, and the ratio AC to DF is equal to BC to FE, BC to FE, and equal to BA to ED. Now we come to the very last part, the SAS, sine and cosine. It means if two triangles have their two corresponding sides in proportion, and the in-between angle equal at the same time, they are similar. That means here, triangle CAB and triangle FDE is an example. Here we have angle A equals to angle D, angle C, angle A equals to angle D, And here we see that DF is equal to 1/2 AC, and DE is equal to 1/2 AB. Yes, this double, and this is double, and so this is double. And angle A is equal to angle D. Okay. In this case, we can see that these two triangles are similar, and all three angles, angle F and angle C equal, angle E and angle B equal. Therefore, if we have AB equals AB over DE, the ratio AB to DE equals to AC to DF, and angle A, the angle in between angle A equals to angle D, then these two triangles are similar. We call this as it is a SAS condition. Sine, angle sine. Now we have seen all the three cases of similar triangles. So after seeing the so many properties and features of triangles, we know that the story of triangle will never end. And there are actually so many to tell about them that we need to have a break here. But before saying goodbye, we would once more like to ask you give us your support and subscribe our channel. Thanks much for your watching. That's the end.